This is the brief on the nature of tensor components and their geometry. Okay, so we're diving into the essential rules for understanding tensors. We're going to focus on how their components, the covariant and contravariant ones, behave mathematically, and what they actually represent physically when you're working with a skewed coordinate system. First up, let's hit the math. What's the deal with mixed tensors? A mixed tensor is just one that has both upper or covariant and lower or covariant indices. The rule for how they transform is actually super simple, but it is critical. The components transform based only on where their index is. Upper indices follow the contravariant rule, and lower indices follow the covariant rule. Simple as that. Second, let's switch over to geometry. What do contravariant components even look like in a skewed system? Think of them as directions on a kind of warped map. They tell you exactly how far to travel parallel to each of those angled grid lines to get to the tip of your vector. They're basically the coordinates. And finally, what about the covariant components? Well, these aren't directions. They're all about direct measurement. Imagine shining a light from way out, perfectly perpendicular to an axis. The covariant component is just the length of the vector's shadow on that axis. It's a projection. Getting this distinction between the transformation math and the geometric picture of parallel versus perpendicular is the key to unlocking tensor analysis.